Hi, today we're going to do a video on distillation equipment, or stills. A couple of years ago, we did a video on a very simple lab distillation, went through some of the principles, and we used that copper alembic still to produce our banana brandy and whiskey videos. So if you're interested in the topic, you might want to take a look at some of those videos. Today what we're going to do is we're going to cover this process, but we're going to take it much, much further. To begin with, distillation is a separation process, but it is not a discrete process. In other words, if you took two containers of water and alcohol, you put them into a flask and you boil this and condense it over into a receptacle. If you boiled all of it away into this container, obviously everything in here would end up in here. Duh. However, it's not a discrete process where you only get the alcohol in the beginning and then only get the water at the end. There's overlap. So every single drop that ends up in that receptacle, from the first all the way through to the last, will have some of everything that is present in here. What causes the separation is time. In the beginning, we tend to get more of the volatiles, and in the end, we tend to get more of the water, or the less volatile material. And what determines that sort of separation and the overlap of those two curves are two principles. One is the absolute vapor pressure of the liquids above the pure compounds. Water has a very low vapor pressure compared to alcohol. It's about only a third of the vapor pressure of alcohol. The reason for that is that water molecules are very sticky. They have a very high van der Waals, or very high intermolecular attraction. That's why it has a high boiling point. Alcohol, not so much. And when you add alcohol to the water, what happens is the alcohol molecules interfere, or essentially shade, the water molecules from each other, limiting the amount of intermolecular attraction and therefore lowering its boiling point, makes it possible for it to vaporize more easily. Similarly, the alcohol is stickier to the water molecules than it would be to other alcohol molecules, effectively raising its boiling point. So the boiling point of the mixed liquid is an intermediate between the boiling point of the two pure liquids. And the percentage of the vapors that are above here are also dependent not only on the absolute vapor pressures, but on the percentages of the liquid here. So what happens is when this boils off, initially we're going to get mostly alcohol and a little bit of water. But as that alcohol is extracted and the water concentration rises here, the boiling point rises, and the percentages of the two components in the flask above, the vapor, also changes. And so eventually we start to produce more and more water and less alcohol. Now the way that we get actual separation is by simply stopping the process. If we boil about half of this away and we end up with about half of the result in the container over here, we're going to have more water left behind and more alcohol over here. If what we then do is we then take what's residual here and throw it out, take what we've produced in the receptacle, put it back in here, and do it again, we'll get a higher concentration of alcohol because we have a higher concentration of alcohol in the mixture. There's going to be a higher percentage of alcohol in the vapor. And we can do this again and again. If we do this once, we might get maybe 65, 70% alcohol over here if we stopped halfway through. If we do it a second time, we might get 80%. Do it a third time, 82, a fourth time, 82.5. And asymptotically, we're going to approach a purer and purer, never reach, but approach a purer 100% alcohol. Now that is effectively what's being done when they use these large pot stills. The Scottish brewers will use huge versions of these alembics, or simple pot stills, to do the distillation of Scotch. The reason that they use this kind of system and they prefer this kind of relatively modest separation is because we don't want to just produce a reagent grade chemical out of here. We want to produce a flavored beverage. So the esters and the aldehydes that are present in the pre-distillate we want some of them to get through the system. So as a result of using a relatively moderate level of separation, we can still retain a lot of the flavors but concentrate the alcohol. Now the design of this kind of distill is pretty obvious. You have a pot, and then you have a bell or an onion top that captures the vapor here and then routes it through this copper tubing to a container here where you can place either municipal water or, wink wink, river water, and cool off the coil that's mounted inside of the chamber, which cools the coil, condenses the vapor, and allows you to collect the output. Now, if you want a little bit better separation, what they will sometimes do, as I just described, is they will take maybe half of the residual here, throw it out or store it, put it aside, take the product of the first distillation, put it back in here again, and repeat the process, increasing the separation, decreasing some of the stronger flavors, and sometimes they'll do this 2 or 3 times to get the kind of separation you want. The problem with this sort of discrete process is that it's wasteful of the material, and it takes a lot of time to clean this out and refill it. It would be nice if you could do this in an ongoing or a continuous process, and that's the purpose of what's called a reflux or Brewhaus column. What this glass blower has done is he's pushed little dimples in this long column here that don't penetrate but increase the internal and external surface area. The external surface area so we have more convective cooling, and the internal surface area so we have more interaction of the vapor and the glass, as well as causing turbulence to cause good mixing of the vapor. What makes this interesting is that when you boil the liquid below here, as we're going to do in just a little bit, the vapor that rises out of here first enters this tube, and because the tube is farther from the heat source, it's a little cooler. So the vapor that enters here selectively will condense some of the water molecules, a little bit more than the alcohol molecules because they have a lower vapor pressure, a higher boiling point. And so as they drip back down here, reflux, that slightly enriched alcohol vapor will rise to the next level here. It will again condense preferentially the water. It will drip back down, and ever increasing concentrations of alcohol vapor will rise through the column until it gets to the top. Eventually, when it gets to this angled bend here, all of the vapor is directed through the condenser where all of the vapor is cooled, changed back into a liquid, and then put into the receptacle over here. This kind of a process is much more efficient and time efficient, and it can increase the concentration of the final product in one pass to maybe 85%, so it saves a lot of time. You can exceed this and produce an even higher concentration by doing 2 things. One, you can slow the heating down, turn the temperature of the heater down a little bit until you're getting just a tiny bit of vapor through here. As a result, you tend to compress these reflux cycles, and you get more cycles occurring here, and you get a higher separation. Alternatively, you could just stack a bunch of these columns on top of each other, giving you much more room for cooling and a larger differential from one side to the other, again enhancing the separation process. The problem with that is that, number one, in the first case, you've got to slow things down, and it might take 6 hours to do the separation. The problem in the second case is you've got a very unwieldy tower that you have to deal with. Now, what I'm going to do is I'm going to fill this thing up, and I'm going to show you how this works. We're going to actually run this. I'm going to show you a neat tool that can be used to sort of calibrate the kind of product that you're producing. Now, this is isopropyl alcohol, and I'm going to fill this column to the top line. And I'm going to use what's called a hydrometer. This is a calibrated float that when it sits into this liquid, it will be supported based on the density. And because alcohol is not very dense, this sinks down a lot lower in this container before it eventually is supported. And you can see that it's up near the top where the numbers represent 100% alcohol, 90% alcohol, 80% alcohol. It's very low down here. This is 91% isopropyl, so it's pretty close. The fact is this is calibrated for a specific temperature, 20 degrees centigrade, and also for ethyl alcohol. So this is not going to be perfectly accurate, but you get the idea. Now, if I were to take this same setup, and we're going to put this into the boiler, And rather than using the alcohol, what we're going to do is we're going to fill this with water. Water to the same mark. This sounds so scientific, doesn't it? Now when I put the float in here, because of the higher density of the water, this doesn't have to submerge as deep before it floats. And you can see that this is sticking way up here around 0% alcohol. So if we now repeat this, pour this in here. And then, just to show you how this sort of can be used to calibrate the amount of alcohol, we're going to fill this halfway up with the alcohol. And then we're going to fill it the rest of the way with the water. And then when I place the float in here, you'll see that it floats at an intermediate position because of the intermediate density here. So it's kind of a neat tool to be used to tell what you're doing as you're doing the distillation process. Now I'm going to pour these liquids in here and the rest of them as well. And then because with a smooth glass boiling flask like this, you can get some pretty big bubbles, I'm simply going to put a little stirring rod in here to help to break up the bubbles, makes it a little less likely to boil over. Turn this on, and then we're going to turn on some heat. And when this gets up to temperature, we're going to see this reflux process proceed. So we'll take a few minutes and let this get warm. So as you can see, the level of this thing is rising very quickly. Notice the temperature here, 18.7. The vapor hasn't gotten here yet. Watch what happens as soon as the vapor gets to this point. Right about here. Bam. See the temperature shoot up as the vapor is beginning to fill up here. And you can see the dripping occurring down here with all of these reflux loops as it's concentrating the alcohol. Now within a minute or so, we're going to get enough condensation in here that will begin filling up the receptacle over here. You can see that the drops are beginning to form. Okay, so let me show you the effectiveness of the distillation process here. Take this off, catch some of the drips. We're going to place it into our cylinder. And remember, it was about halfway supported before when we put the hydrometer down in here. Now we'll see what happens. And you can see how it's floating much deeper, down near the 190 proof. So clearly this does work. Now one of the limitations here, obviously, is that we can't get as high a separation as we might like simply because the height of this column is limited and the amount of differential we have across here is limited. So if we want to carry this further without making it inconvenient, we introduce the next tool, which is called active reflux. So this is a 60-liter active reflux still. We obtained this from a company called Brewhaus in Texas. We'll put a link in the description below. There is another company called Still Dragon that makes even higher end stills that can get all the way up to hundreds of thousands of dollars and thousands of liters of product capacity. But they all work on the same basic principle. The 60-liter container down here, which is full capacity, should only be used up to about 40 liters because you always want a space above any distillation for the bubbling and the churning to occur so that you're not forcing pre-distillate into your reflux column. So this is probably effectively a 40-liter capacity still. If you look down here, you'll see these pressure or spring clamped band heaters that are mounted on the side here. Each one of these is 1,500 watts, And what they do is they provide heat on the lateral walls. And the reason that's important is anybody who's got experience in making something like custard or boiling anything that has a particulate in it, the particulates tend to settle on the bottom. And if all of your heat is coming through those particulates from either a flame or a heater on the bottom, there's a greater chance of scorching the material in here and adding off flavors. So by putting the heat on the lateral walls where the particulates don't tend to settle, and then also spreading out the surface area much larger so that we don't get so much local extreme heating, you minimize that chance of scorching. As you move up here, this is the reflux column, and we'll get into this in a little bit more detail later because it operates on a different principle than the Brewhaus column that I showed you before. What makes this still substantially different is this. This is an active reflux condenser, or a defligmator. And what this does is it cools the hot vapors that come through on the first reflux cycle through this relatively short column. And effectively what it does is it folds the reflux back, because what it does is it condenses the hot vapors and sends them back for another pass through the reflux column. And by being able to precisely adjust with one of these valves the amount of heat that's extracted here, you can either turn this off and effectively remove the reflux condenser property and you have a moderate reflux tower here. Or you can turn this all the way up to max cool and effectively pull all the heat that you sent in originally out up here and create almost an infinite loop of reflux processes, and essentially you get no output. Now that might seem useless, but there is an application to that, and I'll get into that in just a second. In any case, once you move past the reflux condenser, you get to a reducing connection here that has the thermometer that allows us to measure the vapor temperatures that are coming out above the condenser. Then the vapors are then routed back down through the true distillation condenser. And this is where all of the heat is removed, all of the vapors are turned back into liquid, and we get liquid pouring out here. What we then do is we connect onto this a device called a parrot. I guess it's because it sort of looks like a parrot. And the way this works is that the liquid flows down through this pipe and runs to the inner pipe up here. And what this pipe allows you to do is, as the fluid flows over here and into this conical receptacle and then out through the spout here, you end up with a level of liquid in a column that's very similar to the cylinder that we use to measure the specific gravity of the liquid. So if you take this hydrometer that I used before and you float it inside of this column, you can do an ongoing real-time measurement of the density of the liquid that's coming out of here rather than having to cut samples out and constantly remeasure this thing manually. It gives you a good feedback during the process, so it's a nice feature to have on this. Now, another interesting feature of these higher-end stills is what's called a T-connector. If you see this flange on the end of the pipe here, it has a small indentation on the upper surface, which is matched by an indentation on the lower surface of the receiving end over here. This thin silicone gasket then fits inside of this little groove. And when this is placed on the end of this connector here, what this T-clamp does is, because it looks like there's a rectangular groove inside of here, which is actually tapered, as these two flanges meet, this tapered connector, as it pushes down, tends to push the two components together, causing it to lock in very securely. And then when you clamp this around here like this, and then put the T connector on here and tighten it down, you not only get an excellent seal here, but you also get a mechanically very strong connection so that this will hold this in a solid position. This is typically used in a lot of vacuum systems because it's so effective. And as you can see, this same sort of T-clamp is used throughout the entire still, all the way from the top all the way to the bottom. And that allows you to disassemble the entire unit for cleaning, but provide a very good seal and mechanical support during the distillation process. Now, even though we have about 3,000 watts going into the bottom of this thing, Nevertheless, it still takes about a half hour for us to get the 30 liters that I have of liquid in here up to near the boiling point. So let me get the heaters going and we'll get this thing warmed up, and then we're going to get to the really interesting parts of this still. So as you can see, we've had this going for about a half hour and we're beginning to build up some liquid here, and we have these plates loading up with liquid and doing some refluxing. And the vapor, as it's beginning to move upward toward the condensers, I don't want to lose any of the vapor, so what I want to talk to you about now is the cooling system. Distillation depends obviously on heat, and a lot of people focus on heat, but the cooling is very important because obviously we have to condense those vapors into a product. And typically what you'll do in a system like this one is you'll hook up the cooling system to, say, a municipal supply or well water, or you might use a very large radiator, kind of like the hacked computer system radiator cooling system that we use for our lab benchtop unit. The problem with that kind of cooling source is it can vary in temperature depending on the air temperature in the room with a radiator or the time of the year when you've hooked this up to a municipal supply. By varying the water temperature, we vary the water cooling even though you have a continuous flow of liquid. And because of the importance of adjusting the reflux condenser precisely to get just the right amount of folding of our reflux cycles and some pass through a vapor, if the temperatures are varying through the process, you're going to be chasing the valve setting on the reflux condenser, and you're going to be less efficient in terms of capturing the liquid. What I came up with, which I've never seen anybody else do, I think it's kind of clever, is I took advantage of the fact that we have this chest freezer over here. And we'll get a shot of this inside. But what this chest freezer consists of is an inner aluminum liner with the cooling coils. And I took a little bit of Flex Seal and sprayed it on the joints between the aluminum, turning this into a watertight container. And then I filled this with about 110 liters of fresh water and turned on the chest freezer a couple of days ago. And what happens is it begins to freeze water along the cold surfaces of the inside of the chamber. And after about 2 days, I've frozen about half of the water. So I've got ice around the sides, and I've got an inner area in the middle here that contains just water. What's nice about this is as heat is poured out of this unit into the cooling system, the water temperature doesn't change. We simply melt ice and we retain exactly 0 degrees centigrade water continuously through the process. And with about half of the water in here frozen and half as water, we have enough cooling sink in this unit that even though the unit is now turned off, we could run this for about 6 hours, about 3 times as long as you would during any normal distillation, on just the cooling water that's in here. So I don't lose too much product in terms of vapor. I'm going to hook this up and I'll show you how this works in real life. So we got our input here, which is this tubing, and we're going to connect this to a pond or aquarium pump. And then we're just going to sink the pump into this center section where the water is, and then take the 2 output tubes from the reflux and the main condenser and just drop them in there. Then we're going to plug this in and send the water going through the system like this. Meanwhile, what I'd like to talk to you about, though, is these. These are kind of interesting. This is called a bubble plate, and what it consists of is a copper disc with these little crenulated caps that are mounted on top of similar little stubs that are brazed onto the surface here. And the way this works is pretty interesting. On the bottom, vapor is able to pass through these holes and up through the top surface of this plate. Once the vapor rounds the top of this inner cylinder, what happens is the vapor is then forced down through the gap between the cap and between these little crenulated openings on the bottom of each of these caps, and will bubble out. As it does so, the bubbling will allow some of the cooling process to occur and will begin to develop a layer of liquid, as you can see here, above each one of these plates. That liquid will continue to rise until it reaches the top of this little stub here and then pour down into a mirrored cap on the bottom here. This cap also has a stud on the bottom and allows the liquid to fill this cap until it reaches all the way to these little holes here where the liquid begins to drop out. What's elegant about this is it's sort of a one-way valve for liquid and gas. Because of the gas that's coming out of here, the liquid is not able to run into these caps. And because of the liquid layer here, vapor is not able to come up through here. So the vapor is able to come up through these holes and the liquid is able to come down through these holes. And then each of these bubble plates will develop a layer of liquid above them that actually accomplishes the reflux action in a liquid phase rather than a solid. In the Brewhaus column, we depended on the surface area here to provide the cooling of the vapor and the extraction of the water molecules to concentrate the alcohol. In this case, where the actual reflux is occurring is on the inner walls of each of the bubbles. As this cooler liquid here sees this hotter vapor, it will extract from those bubbles a small amount of that water which accumulates in this layer of liquid here. And so the reflux or the concentration is actually occurring in the bubble, not on the surface of the glass. Now you can see this continually moving up here, and you can see the dripping coming from each one of these small little stubs here as the vapor is going up toward the reflux condenser. You can see the temperature up here right now is running at about, what is that, 78.8 degrees. We don't have enough vapor up here at this point to have heated the thermometer, and therefore we're not getting any output here. Another thing that I want to bring up about this bubble plate is the fact that you notice, unlike the entire structure here, which is built out of stainless steel, this is made out of copper, and there's a reason for that. When you ferment any kind of a grain or any kind of a fruit, you will produce a very small quantity of hydrogen sulfide. And hydrogen sulfide is kind of interesting. If you've ever been in a chemistry lab and you smell that stinky smell that smells so smelly, that rotten egg smell, that's hydrogen sulfide. Hydrogen sulfide is almost as toxic as hydrogen cyanide, and in very, very small quantities will create a foul, sort of rotten smell or taste that will get into your final product. And because of the fact that it is a nerve toxin, at very low concentrations you can smell it. But when the concentrations rise high enough, it will actually anesthetize the olfactory nerves and you won't be able to smell it anymore. So as long as it stinks, it's safe. But once you can't smell it anymore, that's when it becomes dangerous. That doesn't really apply here, but it's an interesting material. And how the copper interacts with this is that hydrogen sulfide is absorbed by the copper. It forms copper sulfate on the surface, and hydrogen gas is released. So the copper will actually convert the hydrogen sulfide to something that sticks to the copper plate and removes that flavor. So even when you're using a stainless steel still, you'll always want to have some copper in intimate contact with that vapor in order to absorb the hydrogen sulfide. So when you have a still that doesn't, say, have a complex reflux column like this, you may make it out of copper. That's why they use the copper in the alembics. And also, if you don't have any easy way of adding the copper in a pipe, you can actually place copper mesh or copper tubing, something inside of the column that has contact with the vapor to get rid of the hydrogen sulfide. Now, as this continues to boil, we can see that the temperature moved from about 78 degrees to about 84 degrees as this is continually filtering water. This water coming out of here is now quite warm, and so this unit up here is doing some reflux cycling, but not very much. And when this temperature pops up to about 150, which it will do in about 2 or 3 minutes, we'll start to see some of the output coming up here. Now you can see that the temperature is rising pretty quickly. We're up at about 141 degrees Fahrenheit, 160. Now you can see that the temperature is rising. It's up at 162 degrees Fahrenheit, and you can see we're starting to get some drips down here. So we're getting output. So I'm going to close this valve, and now we'll begin filling this inner chamber in here and looking for an overflow that occurs up here where we can then make our specific gravity measurement. This will take a minute or two. So if you see here, we have a temperature of 170.0 degrees Fahrenheit. And if you look here, you'll start to see that the liquid is reaching the top and beginning to overflow into this conical section here, and then it will soon begin to pour out through the spigot. I can then take advantage of that convenient cylinder, and I'll drop in my hydrometer. And you can see that what we're looking at right now is about 180 in terms of proof. Now, if we slow this down, we can obviously get higher concentrations. If we add another bubble plate, we can obviously get higher concentration, put it back in other words. Or if we turn our Hydrometer or reflux condenser to a little bit more aggressive refluxing, again, we can increase the concentration. But over time, this will continually rise as more and more water is added to the final output. Now, the concentration of this in here, as I said, is about 180 proof. And what's nice about this is frosty cold. Because we are using 0-degree temperature water to cool off this, this is ice cold. And so the product that comes out of here is frosty. As a result, rather than being tepid or room temperature, the very volatile alcohol is less likely to evaporate into the air by using super cold water to do the cooling. It's a big advantage. Another advantage of this type of a system is the fact that you can modify it for different types of applications. For example, let's say that we didn't want super high performance filtration here. What we wanted to do is we wanted to have more like a pot still setup. What you can do is turn the reflux condenser off so we're not folding the reflux cycles in so many times. And then you can actually take an insulator and wrap this around the reflux column like this, essentially turning this from a reflux column into a complicated plumbing system. The vapor doesn't have the chance to reflux, and therefore we've created a pot still out of a reflux column. Very easy to do with a simple piece of insulation. The other thing that you can potentially do is if we turn this to high input for the reflux condenser and basically fold everything back in again and again, we can take advantage of a process called alcohol extraction. When people are making flavored vodkas or they are making gin, what they do is they take the hot alcohol vapors and extract the aroma and the flavors from the botanicals that can be placed into this system with the hot vapor. What you do is you get a segment of pipe. It looks very much like the reflux condenser here in diameter and length. And it can either be inserted here by opening up this gap and putting it in here, or it can be put post-condenser here and expanding this up here. What that does is if you place it up here, the hot alcohol vapor will pass through this segment, which has a perforated stainless steel plate at the bottom and allows you to put botanicals into that container. So if you're making gin, you'd use juniper berries and some cardamom, and depending on your recipe, maybe allspice, lemon peel. And all of those flavors will then be extracted and sent into your final product. If, for example, you want to make a flavored vodka, you could do the same thing. If you want even more powerful extraction and use less of the botanicals, one of the things that you can do is you can place the filtration system, or the gin basket is what that's called, below here, and you'll reflux the hot alcohol vapors again and again and again through the same botanicals, which makes it more efficient, and at the same time will extract less volatile substances and make a stronger extraction. There's a lot you can do with this simple still without doing very much modification of the way that the thing is set up. Now that's basically how this operates, and it's pretty neat and pretty interesting, and we're going to be doing a lot of experiments with this. In the next video, what we're going to do is I'm going to show you how to make flavored rum. So if you like the kind of things that we're doing in these videos, please subscribe. We're growing like crazy, and our next goal is 1 million subscribers, and we'd really appreciate that, because the bigger we get, the more money we get out of YouTube to be able to finance the kind of equipment that we're using for these videos. If anything that I've covered here is not clear or you want more details, Put your questions in the comments section because I read all of them and I try to answer a lot of questions. In addition, it also gives us a lot of ideas for new videos and things that we might want to cover in a little bit more detail. So a lot of fun. I'm going to have a lot of fun with what we're doing here. And please stay safe, have a great afternoon, and we'll see you soon.